In 100 trillion years, the last star will go dark. Not a dramatic explosion, not a flash. Just a slow, quiet cooling into permanent darkness. And that is only where this story begins. There is a number that changes the way you experience every single night sky you will ever look at for the rest of your life. The number is 100 trillion. Written out, it is a 1 followed by 14 zeros. 100 trillion years from now, the final star in the observable universe will exhaust its last hydrogen atom, collapse into a cooling remnant, and end the era of starlight that has been running continuously since before this planet existed. And everything that happens after that is stranger and longer and darker than almost any human being has ever sat still long enough to fully contemplate. We are going to do that tonight. We are going to follow the universe all the way forward, not just to the death of the last star, though we will spend a long time on that, but past it, past the era when even the corpses of stars slowly fall apart, past the era when black holes swallow everything and then, impossibly, evaporate into nothing, past the era when the last photon of Hawking radiation crosses the last empty cubic light-year of a cold, flat, featureless cosmos, and there is simply nothing left to describe. We are going to follow the universe to its actual end, or to what passes for one, and try to understand what that means and why, in the most rigorous physical sense, it should matter to anything that is alive right now. This is not speculation in the loose sense. The physics we are going to work through is grounded in the best cosmological models humanity has ever built. The timeline is derived from equations that have been tested against the oldest light in the universe. There are genuine uncertainties, and we will be honest about all of them. But the broad shape of what is coming is not in serious scientific dispute. The universe has a future, and that future has already been written in the laws of thermodynamics and gravity and quantum mechanics. We are going to read it. Before we go forward, we have to understand where we are right now, because the now matters. Not just because you happen to be living in it, but because the current era of the universe is something so specific, so brief by cosmic standards, and so improbably structured for the existence of things like you and me and every form of complexity that has ever existed, that failing to appreciate it makes everything that comes next harder to understand emotionally. We are living in what cosmologists call the stelliferous era. The word comes from the Latin for star-bearing, and that is exactly what it is, the era of stars. The period in the universe's history when enough hydrogen exists in close enough concentrations that gravity can collapse it into dense, hot, radiating spheres that fuse atoms and release energy for billions of years at a stretch. The stelliferous era began roughly 100 million years after the Big Bang, when the universe had cooled enough and gravity had done enough work that the first stars ignited. Those first stars were monsters by any modern standard, hundreds of times the mass of the sun, blazing blue-white at temperatures tens of thousands of degrees hotter than anything in our current sky. They burned through their fuel in 1 million years or less and died in catastrophic explosions that seeded the universe with the first heavy elements. They were population 3 stars, technically called, and not a single one of them is alive today. Every last one burned so fast and so hot that they are all long dead. From that first lighting of the cosmic hearth to the current moment, the stelliferous era has been running for approximately 13.8 billion years. The sun, your star, the one that powers every biological process happening on this planet right now, is a middle-aged star in the middle portion of this era. It is about 4.6 billion years old and has roughly 5 billion years of main sequence burning left before it begins its own dramatic transformation. The Sun is not old. By the standards of the era it lives in, the Sun is barely halfway done. And that is the key perceptual problem you have to solve before anything else in this story makes sense. When humans think about the future of the universe, we tend to think in the units our nervous systems were built for: days, seasons, human lifetimes, maybe a few generations. The scale that feels intuitively meaningful is something you could plot on a wall calendar or describe in terms of grandchildren and great-grandchildren. When you stretch that intuition toward millions of years, the mind starts to slip. When you reach billions, it flatlines entirely. And the timeline we are working with tonight does not even begin to get interesting until we are measuring time in units that are tens of millions of times longer than the current age of the universe. This is the core challenge of deep time cosmology, and it is worth spending a moment on it explicitly before we proceed. The only honest tool for navigating time at this scale is mathematics, supplemented by analogy where analogy will actually help, and abandoned without apology when it stops helping. We are going to use both, but every time you feel the numbers slipping away from you, every time a figure like 10 to the power of 40 years feels like it just means very large and you lose the sense of it, I want you to notice that feeling and sit with it for a second, because that feeling, that vertiginous loosening of intuitive scale, is itself a piece of data about the universe. It is telling you something real about how far the future extends beyond anything your evolutionary heritage prepared you to contemplate. Let us begin with something that, in this context, qualifies as almost immediate. Roughly 4.5 billion years from now, the Sun will change in a way that makes everything we know about this solar system irrelevant. It will begin to exhaust the hydrogen in its core. Fusion will slow there as the hydrogen supply dwindles. The core will contract under its own weight, heating up as it does, and that additional heat will push the outer layers of the Sun outward in a swelling expansion. The Sun will become a red giant. Its radius will expand to roughly 200 times its current size. Conservative models suggest it will engulf Mercury and Venus. Some models suggest it may reach Earth's current orbital distance, though the story is complicated by the fact that the Sun will also lose mass through its stellar wind during this process. And as a heliosphere loses mass, orbits around it expand outward. Whether Earth is physically swallowed by the expanding solar envelope or whether it drifts just far enough outward to avoid being engulfed directly is a question that depends on details of stellar modeling that remain somewhat uncertain. What is not uncertain is that long before the Sun reaches its maximum red giant size, Earth will be uninhabitable by anything we would recognize as life. The luminosity of the Sun increases continuously throughout its main sequence lifetime. In about 1 billion years, it will be about 10% brighter than it is today, and that increase alone will likely push Earth's climate past a point where complex multicellular life can survive. The oceans will begin to evaporate. The atmospheric chemistry will change. The planet will enter a feedback process of warming that, based on what we observe in Venus today, does not reverse easily. Earth as a habitable world has roughly 1 billion years remaining, give or take the uncertainties in climate modeling. This is not the main subject of tonight's exploration. The death of the Sun and the end of Earth's habitability are prologue. They are the opening act. We mention them not because they are the most dramatic things that will happen, but because they are the most relatable. They are the closest future calamity on a timeline that includes dozens of increasingly unimaginable ones. And they are relevant because they establish something important about the logic of what follows. The Sun is not the longest-lived star in the universe. It is not even close. And understanding why matters enormously for understanding what the universe looks like at the 100 trillion-year horizon. The Sun has about 2 solar masses and burns at a surface temperature of roughly 5,178 Kelvin. Those specifications, mass and temperature, determine how long it can maintain fusion in its core. The relationship between mass and lifespan in stars is counterintuitive on first hearing it. You might expect bigger stars to live longer, the way a larger tree might live longer than a smaller shrub. But stars are not trees. Stars are fusion reactors, and the more massive a star is, the more gravitational pressure is crushing its core, the faster it has to burn to maintain the outward pressure that keeps it from collapsing, and the faster it therefore exhausts its fuel. Massive stars are profligate, low-mass stars are misers. The Sun, at one solar mass, has a total main sequence lifetime of about 10 billion years. Stars 2 or 3 times the mass of the Sun live for only 1 billion years or so. Stars 10 times the mass of the Sun live for only tens of millions of years. The truly enormous stars, the ones 30 or 40 times the mass of the Sun that we see blazing in the most active, star-forming regions of nearby galaxies, live for only a few million years before exhausting their fuel and dying in supernova explosions. Their life cycle is not even a whisper in cosmic time. They are brief, violent, and brilliant. But below the Sun, things change dramatically. Stars, smaller than the Sun, burn so slowly that their lifetimes extend not into billions of years, but into trillions. A star with half the mass of the Sun will live for roughly 50 billion years on the main sequence. A star with a quarter the Sun's mass will live for hundreds of billions of years. And the smallest genuine stars, the ones right at the lower mass limit of stellar fusion, where hydrogen barely ignites, those tiny red dwarfs will burn for something between 1 trillion and 10 trillion years. Some models suggest the very smallest red dwarfs may persist for as long as 10 to 20 trillion years before exhausting their hydrogen supply. To put that in context, the current age of the universe is 13.8 billion years. The most long-lived red dwarfs will outlast the current age of the universe by a factor of more than 1,000. Not a little longer, not twice as long or 10 times as long, 1,000 times longer. Red dwarfs are not exotic. They are not rare. They are the most common type of star in the universe. Approximately 70 to 75% of all stars in the Milky Way are red dwarfs. In the observable universe, they outnumber every other type of star combined by a substantial margin. There are more red dwarfs in the Milky Way alone than there are grains of sand on every beach on Earth. And not a single one of them has ever died of old age. Because the universe is only 13.8 billion years old and the shortest-lived red dwarfs live for at least 100 billion years, every red dwarf that has ever formed anywhere in the observable universe is still alive. Every single one. They are all, in stellar terms, infants and children. None of them has reached middle age yet. This is the reality that defines what the universe will look like at the 100 trillion year boundary. But first, we have to get there. And on the way, many things will change. Let us begin about 4.5 billion years from now. Not with the death of the Sun, which we have mentioned, but with something that happens on a larger scale around the same time, something that has been in motion since before there were eyes to watch it. The Milky Way and the Andromeda Galaxy are currently approaching each other at roughly 110 kilometers per second. Andromeda is approximately 2.537 million light-years away. In about 4.5 billion years, roughly the same time frame as the Sun's red giant phase, Andromeda and the Milky Way will begin their first close pass. The word collision is somewhat misleading because galaxies are mostly empty space. Two galaxies colliding is not like two cars hitting each other. It is more like two swarms of bees passing through each other, with each bee representing a solar system embedded in vast empty distances from every neighboring solar system. The probability that any individual star in the Milky Way directly strikes any individual star in Andromeda during the merger is essentially zero. The distances between stars within galaxies are simply too vast. The Sun is 4.2 light-years from its nearest stellar neighbor. Even during a full galaxy merger, stars pass by each other at distances measured in light-years. No collision, no cataclysm at the individual stellar level. What does happen during a galaxy merger is a thoroughgoing reorganization of the gravitational structure of both systems. Stars that were in stable orbits around the Milky Way's core will be perturbed into entirely different trajectories by the gravitational influence of the incoming Andromeda galaxy. The disk structure of both galaxies will be disrupted. Stars will be flung into new orbits, some wildly eccentric, some out of the plane of the current disk entirely. The gas and dust in both galaxies, the material from which new stars form, will be compressed and disrupted by the interaction, likely triggering a burst of new star formation as cold gas clouds collide and collapse. The two supermassive black holes at the centers of the Milky Way and Andromeda, our own Sagittarius A star with its 4 million solar masses, and Andromeda's central black hole, which may be as massive as 100 million suns, will eventually spiral toward each other and merge in a single catastrophic event that will release an enormous burst of gravitational waves. That merger will produce a new, larger, supermassive black hole at the center of the galaxy that will emerge from the collision, a merged structure that astronomers sometimes call Milkomeda in anticipation. This entire process, from first pass to complete merger, will take several billion years to play out. The resulting galaxy will be a single elliptical galaxy, lacking the disk structure and spiral arms of both progenitors. It will be quieter, rounder, with most of its gas consumed or expelled, its star formation rate declining. The night sky, as seen from any surviving planet in either galaxy, will change beyond recognition over the course of this merger. New constellations will be born and old ones destroyed. Andromeda's disk, currently visible as a smear of light in the autumn sky from dark locations, will grow and distort and eventually dissolve into the merged structure that surrounds us. But here is the thing about the Milkomeda merger that matters most for the story we are telling. In the scale of what we are describing, even this enormous galactic collision is early. It is happening while the universe is still young, while star formation is still vigorous, while the basic structure of the cosmos, clusters of galaxies slowly merging within their local groups while the space between those groups expands, is still largely intact, because the universe is expanding, and the expansion is not slowing down, it is accelerating. This is the most important cosmological fact discovered in the last 100 years. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and one by Brian Schmidt, published observations of distant type Ia supernovae that agreed on a result that contradicted all expectations. The universe is not expanding at a steady rate, that gravity is gradually decelerating. The universe is expanding faster and faster. The rate of expansion is increasing. Something is driving it apart with a force that grows stronger as the universe gets larger. That something is called dark energy. We do not know what it is. We know it exists because the observations demand it. We know it constitutes roughly 68% of the total energy content of the observable universe. We know that in the current cosmological model, it behaves like a cosmological constant, a fixed energy density of empty space that does not dilute as the universe expands but remains constant or possibly increases in density, exerting a repulsive influence on the expansion that accumulates with the sheer volume of space involved. The consequences of this accelerating expansion for the far future are profound. Every galaxy that is not gravitationally bound to the Milky Way within our local group is already being carried away from us by the expansion of space. Most galaxies are already retreating from us faster than light can cross the growing distance between us and them. The light they emit right now is, in many cases, already doomed never to reach us, because the space between us and their source is expanding faster than light itself can travel. This is called the cosmological event horizon. It sits at approximately 16 to 17 billion light-years from us. Anything beyond that distance right now is, in a strict causal sense, already gone, already cut off from any future contact with the Milky Way, regardless of what happens here or there. Not because the matter has been destroyed, but because the geometry of an accelerating, expanding universe creates a boundary beyond which no signal, no light, no gravitational wave, no particle of any kind can ever reach us. And that horizon is moving. It is moving toward us, not in the sense that it is physically approaching us through space, but in the sense that as time passes, more and more of the universe gets pushed beyond that causal boundary. More and more galaxies that we can currently see fall off the observable edge and become permanently unreachable. The catalogue of galaxies available to any future civilization observing from our location is shrinking. In about 100 billion years from now, things like roughly 10 times the current age of the universe, the situation will have changed dramatically. Almost every galaxy that is not gravitationally bound to the Milky Way within our local group will have receded beyond the cosmological event horizon. The sky, from the perspective of any astronomers who might exist in the merged Milky galaxy at that time, will have changed. The galaxies that we can currently see in our sky, the 2 trillion or so observable galaxies spread across billions of light-years, will, for the most part, be gone. Not destroyed, just gone, carried beyond the reach of light by the relentless expansion of space. The night sky, as seen from Milky 100 billion years from now, will contain mostly the galaxies of our own local group, all merged by then into a single, large structure, surrounded by increasing darkness. But stars will still be shining. The stelliferous era will not end at 100 billion years. It will be waning, its star formation rate having declined substantially from its peak. But it will not be over. Stars will still exist. Light will still pour from their surfaces. Fusion will still be converting hydrogen to helium in stellar cores. The universe will still look, in some important respects, like a universe. And then, gradually but inexorably, the lights will start going out. Let us now think carefully about what happens as we approach the 100 trillion year mark, because this is the horizon that gives this story its title. 100 trillion years, 10 to the 14th power, the approximate end of the stelliferous era. What actually happens at this boundary is not a single event. It is not like the lights flickering off all at once across a city during a power failure. It is more like a very long twilight that stretches across tens of trillions of years, during which the universe becomes progressively dimmer, quieter, and cooler, with the last light fading so slowly that no observer embedded in the process could easily mark a moment and say, "This is when the stars ended." To understand the twilight, you need to understand what fuels stars. Stars are powered by nuclear fusion. Specifically, in the main sequence phase that makes up the bulk of a star's life, they are powered by the fusion of hydrogen nuclei into helium nuclei. 4 hydrogen nuclei, 4 protons, fuse together through a series of reactions to produce 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and a release of energy in the form of gamma radiation and kinetic energy in the nuclei produced. That energy, working its way outward through the star over hundreds of thousands of years, eventually reaches the stellar surface and radiates into space as the light and heat we observe. The key constraint is the hydrogen supply. Stars cannot manufacture their own fuel. They can only burn what they were born with, plus what they might accrete from their surroundings over their lifetimes. A star's lifespan on the main sequence is essentially a calculation of how long its initial hydrogen supply lasts at the rate it is being consumed by fusion in the core. Now, there is a critical distinction between how different mass stars handle their hydrogen. The Sun and stars like it have a core where fusion occurs, surrounded by layers that are partially stable against convection. In a Sun-like star, the hydrogen in the core gets used up over the star's lifetime, but the hydrogen in the outer layers does not circulate efficiently into the core to replenish it. The core can only use what is immediately available in the high-temperature, high-pressure zone at its center. This is part of why Sun-like stars, when they exhaust their core hydrogen, do not simply extinguish. They enter the red giant phase, restructuring dramatically as the core shrinks and heats, while the outer layers expand. Red dwarf stars are fundamentally different in this regard. They are fully convective. The entire volume of a red dwarf, from surface to core, circulates constantly through convection. This means that hydrogen from the outer layers continuously mixes down into the core, providing fresh fuel. A red dwarf star does not just use the hydrogen in its core. It uses essentially all of the hydrogen in its entire body, mixing it in over its multi-trillion-year lifetime. This is one of the primary reasons red dwarfs live so much longer than Sun-like stars. They are more efficient. They burn the whole tank, not just the fuel that happens to be in the combustion chamber at any given moment. The smallest red dwarfs, with masses around 0.8 to 0.1 solar masses, burn their hydrogen so slowly and so completely that they may persist as fusion-powered stars for 10 trillion years or longer. Some theoretical models extend the lifetimes of the very smallest red dwarfs to nearly 20 trillion years or more, though these estimates have significant uncertainty at the long end because no red dwarf has ever aged past the hydrogen-burning phase in the history of the universe. They are all still young. We are extrapolating. So what does the universe look like when you are at, say, 1 trillion years, 10 times the current age of the universe and still well within the stelliferous era by any definition? The large, bright, sun-like stars are long dead. Every G-type star, every F-type star, every A-type star, every star with more than roughly half a solar mass has exhausted its hydrogen and moved through its post-main sequence evolution. The sky has lost its most spectacular performers. No more blue supergiants blazing at 10,000 times the sun's luminosity. No more giant stars puffed to hundreds of times the sun's radius. No more supernova explosions scattering heavy elements into the interstellar medium, because the stars massive enough to explode as supernovae are all long gone. What remains at 1 trillion years is primarily red dwarfs. Dim, cool, stable red dwarfs burning patiently at fractions of the sun's luminosity, radiating mostly in the infrared and deep red portions of the spectrum, and the remnants of the stars that have already died. White dwarfs, the dense, cooling cores of stars like the sun that have shed their outer layers and settled into a slowly cooling crystalline state. Neutron stars, the even denser remnants of stars massive enough to have exploded as supernovae but not quite massive enough to have collapsed entirely into black holes. Brown dwarfs, objects that formed like stars from collapsing gas clouds but never accumulated enough mass to ignite sustainable hydrogen fusion, sitting cold and dim somewhere between star and gas giant planet. The interstellar medium, the gas and dust between stars that serves as the raw material for new star formation, will be significantly depleted by 1 trillion years, not gone, but reduced. The great molecular clouds that currently sprawl across the galaxy full of cold hydrogen and complex organic molecules are being consumed by star formation and disrupted by stellar evolution. Each new star that forms takes gas from the interstellar medium. Each supernova and planetary nebula expels some gas back, enriched with heavy elements. But the net trend is consumption. The interstellar reservoir shrinks over time. As the reservoir shrinks, new star formation slows, and this slowing has already begun. The peak of cosmic star formation occurred roughly 10 billion years ago, when the universe was only about 3 to 4 billion years old. Since then, the rate of star formation across the observable universe has been declining. We are already past the golden age of star birth. We are living in the declining phase. The universe is already gradually dimming, just on timescales too slow for human civilization to notice. At 10 trillion years, the decline has accelerated. Most galaxies have consumed the bulk of their free gas. Star formation is sporadic, dependent on whatever gas can be recaptured from stellar winds or whatever cold clouds survived in the outer reaches of galactic halos. The universe at 10 trillion years is quieter and redder than it is today. Most of its visible light comes from red dwarfs, which are individually so faint that even the combined output of all of them represents a diminished total luminosity compared to the universe of today. The brilliant, hot, short-lived stars that dominate the visible spectrum of the current universe are absent. There are no new, massive stars. There are no supernova explosions happening on a regular basis across the galaxy. There may be isolated supernovae still occurring as white dwarfs in binary systems occasionally accrete enough mass from a companion to exceed a critical mass limit and detonate in what we call a Type Ia supernova, but these events are becoming rarer. The universe is calmer. This trend continues to accelerate as we approach the 100 trillion year boundary. At 50 trillion years, the population of active stars has shrunk dramatically. The heavier red dwarfs, those with masses around 0.3 to 0.5 solar masses, are beginning to exhaust their hydrogen. Some of them are entering their final phases. A red dwarf dying is nothing like a sun dying. There are no red giant phases for most red dwarfs. Instead, they simply get bluer and hotter as they use up their hydrogen and the core contracts, passing through what astronomers call a blue dwarf phase, then fading into white dwarfs. It is a quiet death by astronomical standards. No dramatic expansion, no planetary nebula flung into space, just a gradual dimming and transition. The population of white dwarfs is growing. These small, dense, Earth-sized remnants retain heat for an extraordinarily long time, but they are not generating any new energy through fusion. They are cooling, radiating their stored thermal energy into space. A freshly formed white dwarf has a surface temperature of tens of thousands of Kelvin. Over trillions of years, it cools. The cooling is slow, much slower than you might expect from a hot object, because the thermal conductivity of the degenerate electron matter inside a white dwarf is very low. But the cooling is continuous and inexorable. At 100 trillion years, the event horizon approaches. The last star formation, in the models that have been worked out by Fred Adams and Gregory Laughlin, and others who study stellar populations and galaxy evolution on these timescales, ends somewhere around 10 to the 14th years, 100 trillion years. At this boundary, all the free gas that could form new stars has been consumed. The molecular clouds are gone. The reservoir that feeds starbirth is empty. Whatever stars exist at this moment are all the stars there will ever be again. No new ignitions. No new fusion reactors switching on in the darkness. The star-forming factories of the universe have closed their doors for the last time. This is the end of the stelliferous era. The question that should immediately arise is what this moment actually feels like, insofar as it feels like anything. And the answer is that it does not feel like anything in particular, because there is no single moment of ending. The 100 trillion year boundary is not a cliff edge. The last star to form does not announce itself. There is no cosmic gong. The transition from the stelliferous era to what comes next is gradual, almost to the point of imperceptibility. The last few red dwarfs forming in whatever cold pockets of gas remain in the outer reaches of whatever galaxies survive will do so without ceremony, flickering on in the dark and burning for their allotted trillions of years while the universe around them grows steadily colder and emptier. But there is something worth marking about this boundary nonetheless. It is the last time in the history of the universe that nuclear fusion in stellar cores will serve as a primary source of free energy. The last time that the burning of hydrogen into helium will pump light and heat into the cosmos and maintain the thermal gradients that allow for the existence of complex structures and the dissipation of free energy that thermodynamics requires for anything interesting to happen. After the last stars die, the universe enters a new and very different mode. What comes after the stelliferous era has been given a name that I find both technically accurate and somehow philosophically appropriate. It is called the degenerate era. The word degenerate here is a technical term from physics, not a moral judgment. It refers to degenerate matter, which is a state of matter found in extremely dense objects like white dwarfs and neutron stars, where the normal rules of classical physics break down and the behavior of the material is dominated instead by quantum mechanical effects, specifically by the Pauli exclusion principle, which prevents any two electrons or any two neutrons from occupying the same quantum state simultaneously. This quantum mechanical pressure, called degeneracy pressure, is what supports white dwarfs and neutron stars against further gravitational collapse. It is what makes them stable even though they have no internal fusion to hold them up. The degenerate era begins when the last actively burning stars exhaust their hydrogen and fade. It is populated primarily by four types of objects: white dwarfs, the slowly cooling remnants of stars like the Sun; brown dwarfs, the substellar objects that never achieved fusion; neutron stars, the dense remnants of stars that exploded as supernovae; and black holes, both the stellar mass black holes left behind by the most massive stars and the supermassive black holes at the centers of galaxies. The degenerate era is, in Adams and Laughlin's cosmological decade framework, defined as cosmological decades 15 through 37, which corresponds to time scales of roughly 10 to the power of 15 years, all the way up to 10 to the power of 37 years. Let us sit with what that means. Cosmological decade 15 is 10 to the power of 15 years, which is 1 quadrillion years, 10 million times the current age of the universe, and by the standards of the degenerate era, that is the beginning, the early stages. The degenerate era stretches from there to 10 to the power of 37 years. Cosmological decade 37, a number so large that writing it out in decimal notation would require pages. During this era, the dominant physical processes are not fusion, not electromagnetic radiation from burning stars, but something slower and quieter. Gravitational interactions, the slow rearrangement of matter under gravity, the cooling of stellar remnants, and, according to some theories of particle physics, the gradual decay of the protons themselves. But let us start with what is better understood. The white dwarfs are cooling. Every white dwarf that forms starts with a stored reservoir of thermal energy. The degenerate matter inside it holds heat extraordinarily well. The cooling is slow. A white dwarf that has been cooling for billions of years, like the oldest ones we can observe today, have surface temperatures of around 3,000 to 4,000 Kelvin, still hot by human standards, still radiating, but much cooler than when they first formed. The cooling continues over trillions of years, then tens of trillions, then hundreds of trillions. White dwarfs slowly leak their stored heat into the surrounding darkness. Their surface temperatures decline, their luminosities drop. The light they emit shifts from the white-blue of a freshly formed white dwarf through yellow and orange and red and finally into the infrared, invisible to human eyes, but still carrying tiny amounts of energy. In the framework of the models we have, the oldest white dwarfs, those that formed very early in the universe's history, from the deaths of the first sun-like stars, will reach very low temperatures after tens of trillions of years of cooling. The models suggest that after roughly 1 to 2 times 10 to the power of 15 years, or about a quadrillion to 2 quadrillion years, the oldest white dwarfs will have cooled to temperatures below a few thousand Kelvin, becoming dim infrared emitters. What happens next is theoretically uncertain but physically inevitable. As a white dwarf cools below a certain temperature, roughly around 12,000 Kelvin, based on current models, the carbon and oxygen nuclei inside it begin to crystallize. The degenerate matter undergoes a phase transition from a liquid-like state to a crystalline solid. The carbon inside a sufficiently cool white dwarf literally forms a crystal lattice. The white dwarf becomes, in the most precise physical sense, a diamond, an enormous crystal of carbon and oxygen, roughly the size of Earth, with a mass between 50% and 120% of the Sun's mass, embedded in degenerate electron matter. This crystallization was actually confirmed observationally in 2019, when astronomers using the European Space Agency's Gaia Space Telescope identified a population of white dwarfs in our galaxy whose luminosities and temperatures matched precisely the theoretical signature of white dwarfs undergoing crystallization. They found hundreds of thousands of white dwarfs that appeared to be in the process of releasing latent heat as their carbon and oxygen cores crystallized, creating a pause in their cooling curve exactly where models predicted it. As the degenerate era unfolds over trillions and quadrillions of years, the cooling white dwarfs become progressively dimmer and cooler until they can no longer be called white dwarfs at all. When a white dwarf has cooled below a few hundred Kelvin, it emits essentially no visible light. It is a dark object supported by electron degeneracy pressure against gravity, radiating so feebly in the far infrared that detecting it from any significant distance would be essentially impossible with any instrument we can currently conceive. These fully cooled white dwarfs are called black dwarfs. They are theoretical objects. No black dwarf has ever been observed because the universe is not old enough for any white dwarf to have cooled to that state yet. The cooling time required to produce a black dwarf from even the oldest white dwarfs vastly exceeds the current age of the universe. But they will form, given enough time, in the degenerate era. A black dwarf is one of the strangest objects in the taxonomy of eventual cosmic objects. It is not a black hole, it has no event horizon. Gravity has not overwhelmed the degeneracy pressure. It is just cold, just dark, a dense, inert, crystalline sphere of carbon and oxygen, sitting silent in the void, carrying no significant free energy, emitting no significant radiation, interacting with the surrounding universe through gravity alone. The universe in the degenerate era will eventually be populated by vast numbers of these objects. All the white dwarfs that form from the deaths of sun-like stars over the entire stelliferous era will, given enough time in the degenerate era, cool into black dwarfs. The Milky Way alone is estimated to contain several 100 billion white dwarfs accumulated over its history. Every single one of them will, given sufficient time, cool into a black dwarf. But here is a question that physics raises at this point, a question that haunts the degenerate era and whose answer determines in principle whether the matter in these cooling objects survives intact for truly astronomical timescales, or whether it quietly dissolves. Do protons decay? The proton is the nucleus of the hydrogen atom and one of the fundamental constituents of all ordinary matter. Everything made of atoms, which is to say, everything physical that you have ever encountered, everything you have touched or seen or tasted or built, is made substantially of protons and neutrons and electrons. The electrons orbit the nucleus. The nucleus consists of protons and neutrons. The protons are what give the nucleus its positive charge and therefore its identity as a particular chemical element. In the standard model of particle physics, protons are stable. They do not decay. A proton will remain a proton forever unless it is involved in some interaction that converts it into something else. The Standard Model provides no mechanism for spontaneous proton decay, but the Standard Model is widely believed to be incomplete. It is an extraordinarily successful theory, confirmed by thousands of experimental results to extraordinary precision. But it does not include gravity. It does not explain the matter-antimatter asymmetry of the universe, the reason why there is any matter at all, rather than equal amounts of matter and antimatter that would have annihilated each other. It does not unify the strong and electroweak forces into a single framework. Theories that attempt to go beyond the Standard Model and achieve some degree of unification, the so-called grand unified theories or GUTS, generally predict that protons should decay. The mechanism varies by theory, but the basic idea is that at the energy scales where the strong nuclear force and the electroweak force are unified into a single interaction, there should be processes that can convert quarks into leptons and vice versa. A proton consists of 3 quarks. If quarks can convert into leptons, then a proton can decay into lighter particles. The most commonly predicted decay channel is a proton decaying into a positron and a neutral pion, which itself quickly decays into 2 photons. The experimental limits on proton decay are extraordinary. Physicists have been searching for proton decay since the 1980s in large underground detectors filled with enormous volumes of ultra-pure water, monitored by thousands of sensitive photodetectors. These experiments can monitor something on the order of 10 to the 33 protons simultaneously, watching for any single one to decay. None have been observed. The current experimental lower bound on the proton lifetime, assuming the most common gut-predicted decay channel, is roughly 10 to the 34 years. The proton, if it decays at all, lasts for at least 10 to the 34 years. That is about 1 billion trillion years, 10 million times longer than the current age of the universe, an almost incomprehensibly long time. But notice what that means. It does not rule out proton decay. It just pushes the time scale deeper into the future. And the degenerate era extends to cosmological decade 37 to 10 to the 37 years, which is 3 orders of magnitude beyond that experimental limit. If guts are right about proton decay, it will occur during the degenerate era. And if it does, the consequences are dramatic. Every proton in every black dwarf, every proton in every neutron star, every proton in every remaining asteroid and planet-like object will eventually decay. The material that black dwarfs are made of will slowly, over geological times, multiplied by factors of millions, convert into leptons and photons. The crystalline interiors of cooling white dwarfs and black dwarfs will be eaten away, proton by proton. The stars that died and crystallized will dissolve, not dramatically, not in an explosion, but in a slow statistical process of quantum mechanical decay that will, over a time scale of roughly 10 to the 37 to 10 to the 40 years, erase all normal matter from the universe. If proton decay occurs, black dwarfs do not survive the degenerate era. They dissolve. If proton decay does not occur, if the proton really is stable, then black dwarfs have an entirely different fate, which we will return to shortly. The neutron stars also cool during the degenerate era. Neutron stars, the remnants of massive stars that exploded as core collapse supernovae, are even denser than white dwarfs, with masses of roughly 1.4 to perhaps 3 times the mass of the Sun crammed into a sphere only about 20 kilometers across. Their interiors consist of neutrons packed so densely that exotic phases of matter may exist, including possibly strange quark matter or other hypothetical dense states. A freshly born neutron star has a surface temperature of hundreds of billions of Kelvin. Over time, it cools through a variety of mechanisms, radiating from its surface and losing energy more rapidly in its first million years than it will for the billions that follow. Over the timescales of the degenerate era, Neutron stars cool to very low temperatures as well. Their fate depends also on whether proton decay occurs. Neutrons, being made of quarks, would also decay if quarks can convert to leptons, though on roughly the same timescale as protons. If proton and neutron decay occurs, neutron stars dissolve along with black dwarfs. But the dominant objects in the degenerate era, the things that accumulate mass while everything else fades and cool, are the black holes. Black holes are unique among all the objects we have been discussing in that they do not cool in any ordinary sense. They do not have a surface temperature in the way a star or a white dwarf does. They do not have interior heat stored from a prior era of fusion or formation. Their mass is, in a sense, their energy encoded in the curvature of space-time rather than in the thermal motion of particles, and they accumulate more mass rather than losing it, at least in any environment where there is infalling material to be consumed. During the degenerate era, the supermassive black holes at the centers of galaxies continue to grow. As stars in galactic cores get tidally disrupted and consumed, as the remnants of stellar evolution scatter through the galaxy, and some are gravitationally focused into the central black hole over time, these already enormous objects get larger, slowly, much more slowly than during the active quasar era of galactic evolution, which is now billions of years in the past, but continuously. Stellar mass black holes, those with masses of perhaps 5 to 100 solar masses, formed from the deaths of the most massive stars, also persist. They do not significantly grow during the degenerate era without nearby infalling material, but they do persist, and they wander through the dark, cold galaxy. There is a process that operates during the degenerate era that slowly strips mass from galaxies. It is called gravitational evaporation, and it is the long-time evolution of a cluster of gravitating objects through gravitational interactions. In a galaxy, stars and stellar remnants undergo repeated close gravitational encounters, tiny tugs and deflections accumulating over billions and trillions of years. The net statistical effect of these encounters is that some objects gain energy and some lose it. The ones that gain enough energy are ejected from the galaxy altogether, flying off into intergalactic space. The ones that lose energy sink inward, falling toward the central black hole. Over a timescale of roughly 10 to the 23 years, gravitational evaporation is expected to completely dissolve the stellar populations of galaxies. Every star, every white dwarf, every black dwarf, every neutron star in a galaxy will either be ejected into intergalactic space or will fall into the central supermassive black hole. The galaxy as a coherent, gravitationally organized structure will cease to exist. What remains will be a massive central black hole surrounded by a dispersed halo of ejected objects flying alone through the darkness of intergalactic space. The galaxies end not with a bang, but with a statistical process. The slow, patient reshuffling of gravitational energy until every object has either escaped the system or been swallowed. By the time cosmological decade 23 arrives, roughly 10 to the 23 years into the future, the familiar structures of galaxies are gone. There are no spiral arms. There are no galactic disks. There are no star-forming regions, of course, since the stars themselves are all dead or dying, but there are not even the large-scale structural organizations of matter that we associate with galaxies as entities. There are black holes growing slowly from whatever material has fallen in. There are isolated cooling objects, black dwarfs and neutron stars and dark matter halos drifting through the enormous volumes of cold, dark space. And there is the cosmic web, the large-scale structure of the universe, but even that is being stretched thin by the continued expansion of space. If proton decay occurs, the very substance of black dwarfs and neutron stars is dissolving during this era, the degenerate era slowly converting normal matter into radiation. The universe is becoming poorer in baryonic matter and richer in low-energy photons and neutrinos. The particles that make up everything you have ever touched or seen are slowly turning into light. If proton decay does not occur, then black dwarfs and neutron stars persist intact through the degenerate era. They are cold, they are dark, they emit no significant radiation, they drift alone in expanding space, but they exist. The matter is still there, crystalline and frozen and silent, waiting. Either way, by the end of the degenerate era, the universe is entering a qualitatively different state, one in which the primary objects of interest, the primary concentrations of mass and energy, are no longer made of ordinary matter, but are instead black holes. The universe is entering what Adams and Laughlin call the black hole era. The black hole era. 10 to the 40th years. One followed by 40 zeros. The beginning of what may be the longest-lasting coherent era in the history of the universe. The black hole era spans from roughly 10 to the 40th years to 10 to the 100th years, which is 10 to the 100 power, known as a googol of years, one followed by 100 zeros. It is very difficult to convey in language what a googol of years actually represents. There is a comparison that might help, though it too strains understanding. The number of atoms in the observable universe is estimated at roughly 10 to the 80 power. A googol is 10 to the 100th power. A googol is 10 billion times larger than the number of atoms in the observable universe. If every atom in the observable universe were itself an observable universe, the total number of atoms in that meta-universe of universes would still be smaller than a googol. The black hole era spans this entire range of time, and during all of it, the dominant objects in the universe are black holes. Let us think about what is happening to those black holes. Radiation. Stephen Hawking showed in 1974 through a calculation that combined general relativity and quantum mechanics in a way that remains one of the most remarkable theoretical results in the history of physics, that black holes are not perfectly black. They radiate. The process, now called Hawking radiation, arises from quantum mechanical effects at the event horizon of a black hole. The basic idea is that the quantum vacuum, the seething background of virtual particle pairs that quantum field theory tells us pervades all of empty space, is perturbed at the event horizon in a way that results in the net emission of radiation. One member of a virtual particle pair falls into the black hole while the other escapes as real radiation. The black hole loses energy equivalent to the energy carried away by the escaping particle. The rate of Hawking radiation is inversely proportional to the square of the black hole's mass. This means larger black holes emit Hawking radiation more slowly. A stellar mass black hole of 10 solar masses emits Hawking radiation at a temperature of about 6 billionths of a Kelvin and will take roughly 10 to the 74th years to completely evaporate. A more massive black hole takes longer in proportion to the cube of its mass. The supermassive black holes at galactic centers with masses of millions to billions of solar masses will take far longer. The Milky Way's central black hole, Sagittarius A star, with its 4 million solar masses, will take roughly 10 to the 87th years to evaporate. The largest supermassive black holes, those with masses of tens of billions of solar masses found in the most massive elliptical galaxies, will take something on the order of 10 to the 100th years, roughly a googol of years, to fully evaporate. These timescales span the entire black hole era. Smaller black holes evaporate earlier, larger ones later, the entire range from 10 to the 40 years to 10 to the 100 years approximately, matching the span of the era as defined by Adams and Laughlin. The black hole era is, in essence, the era during which black holes evaporate. But what does it look like? What is the universe like during this time? It is almost entirely dark. There is essentially no baryonic matter left in the universe by the black hole era, either because proton decay has converted it to radiation over the degenerate era, or because it has all been consumed by black holes during galactic processes over the enormously long time scales involved. The black holes themselves are the dominant objects. They are not shining in any conventional sense. Their Hawking radiation is at temperatures so low as to be essentially undetectable. A stellar mass black hole, one that has not yet evaporated, has a Hawking temperature of billionths of a Kelvin. The cosmic microwave background radiation, the remnant of the Big Bang now cooled by billions of years of cosmic expansion, is currently at about 2.7 Kelvin. By the time of the black hole era, the cosmic microwave background will have cooled to temperature so low as to be essentially zero. The ambient temperature of the universe will be extraordinarily close to absolute zero. But a black hole with a Hawking temperature of billionths of a Kelvin is still cooler than the ambient temperature of the universe in the early degenerate era, because the cosmic microwave background is warmer. This means that in the early degenerate era, black holes are actually absorbing more energy from the cosmic microwave background than they emit through Hawking radiation. They are gaining mass, not losing it. It is only as the universe expands and the background radiation cools below the Hawking temperature of a given black hole that the Hawking evaporation begins to dominate and the black hole starts to lose mass. As a black hole evaporates, it gets smaller and hotter. The Hawking temperature is inversely proportional to mass. As mass decreases, temperature increases. The process accelerates as the black hole shrinks. In the final stages of evaporation, the last moments of a black hole's existence, the Hawking radiation becomes extremely energetic. The black hole, now tiny, emits a brief burst of high-energy particles and radiation as it reaches the Planck mass, around 22 micrograms. What happens at this point is one of the genuine unknowns of theoretical physics. We do not have a theory of quantum gravity that we can use to reliably describe the final moments of black hole evaporation. The classical general relativistic description breaks down. The quantum mechanical description in its current form does not extend to this regime cleanly. Various proposals exist. Some suggest a remnant forms, some suggest complete evaporation into thermal radiation, some suggest a brief naked singularity. For the purposes of the broad outline of the universe's future, the details of the final Planck mass evaporation are less important than the overall fact that the black hole converts its mass into radiation and thermal particles and then is gone. The mass that was locked in the black hole, which may have included mass originally from stars and gas and planets and living organisms and every other form of matter that fell in over the black hole's long life, is converted into radiation and scattered through the universe. Every black hole in the universe, from the smallest stellar remnant to the largest supermassive colossus, will eventually evaporate. By the time the largest supermassive black holes have finished evaporating, by the time we have reached cosmological decades approaching 100, the universe will contain essentially no black holes. The objects that dominated the black hole era, the only significant concentrations of energy and mass remaining in the universe, will be gone. What remains? What remains after the last black hole has evaporated is something that cosmologists call the dark era, and it is not easily described because almost nothing is happening in it. The dark era is the era that follows the black hole era. Cosmological decade 100 and beyond, 10 to the 100 years and beyond. It is an era defined almost entirely by absence. There are no stars, no white dwarfs, no black dwarfs. If proton decay occurred and dissolved them, no neutron stars, no black holes, no significant clumps of matter of any kind. What persists is a thin, extremely cold, extremely diffuse gas of elementary particles, photons flying through the expanding space, neutrinos drifting on near infinite paths, electrons and positrons, if they have not all annihilated with each other over the preceding unimaginable spans of time. Possibly gravitons if gravity has quanta. The products of all the Hawking radiation from all the black holes that ever existed now spread over volumes of space so vast that the average density is effectively zero. The temperature of the dark era is extraordinarily close to absolute zero, but never quite reaching it, because the Hawking radiation from the last evaporating black holes contributes some residual thermal energy to the universe, and because there are still quantum fluctuations in the vacuum that maintain a tiny but non-zero temperature. The universe settles into a state that is sometimes called the heat death or the big freeze. The concept of heat death does not mean the universe becomes hot, it means the opposite. It means thermodynamic equilibrium is approached. In thermodynamics, heat is not temperature, but rather the flow of energy from hotter to cooler regions. Heat death is the state in which there are no longer any temperature gradients anywhere, no hot spots or cold spots, no concentrations of free energy that can do work. Everything is at the same featureless temperature everywhere. No energy flows, no work is done, no processes occur that have any directionality, any before and after, in a meaningful sense. The heat death of the universe is the maximization of entropy. Not because something dramatic happens, but because over the enormous spans of time in the dark era, quantum processes and the residual particle interactions that still occur, even at near absolute zero temperatures, gradually erase all gradients and distribute all available energy with perfect uniformity. The thermodynamic arrow of time, the sense in which one direction is the future and the other the past, disappears. In a universe in perfect thermodynamic equilibrium, there is nothing to mark the passage of time at all, nothing to distinguish one moment from the next, nothing to count events by. The universe in the dark era is not just empty. It is quiet in a profound physical sense. It is a state of such thoroughgoing equilibrium, such complete absence of gradients and flows and free energy, that the concept of time itself becomes ambiguous. There is no river of time to travel along. There is just the static, cold, featureless maximum entropy state extending in all directions forever. And here we reach the edge of what physics can currently say with confidence. Not because the physics is uncertain in the way that gut-scale proton decay is uncertain, but because the final state of the universe in the heat death scenario is one where the concepts we use to describe physical processes become empty. There are no processes, there is no sequence of events. There is just the state persisting, if that word even applies, without change. But there is a deeper question hidden in this picture that deserves attention before we move on. A question raised by the extension of the same cosmological model that predicts the heat death, and it concerns something called the Boltzmann brain. Ludwig Boltzmann was one of the 19th century's greatest physicists, the founder of statistical mechanics, and the man who gave us the thermodynamic interpretation of entropy. And late in his life, working through the implications of his own equations, he confronted a paradox that genuinely disturbed him and that is still discussed in modern cosmology today. The paradox goes like this. In a universe that extends forever in time and that maintains some small, non-zero temperature, and therefore some ongoing thermal fluctuations, statistical mechanics guarantees that any finite configuration of matter will eventually appear as a spontaneous fluctuation from the thermal background, not with any regularity, not predictably, but in an infinite time. Any physically allowed configuration has a non-zero probability of fluctuating into existence, and in infinite time, non-zero probability means eventual occurrence. This includes, theoretically, fluctuations that produce complex structures, including, at the extreme end, fluctuations that spontaneously produce a complete, fully functional brain, with memories and experiences and the subjective sense of existing. A structure complex enough to have a conscious experience arising entirely from a random thermal fluctuation in an otherwise featureless maximum entropy universe. Such a fluctuation would be extraordinarily rare. far rarer than any normal process we have described, but in infinite time extraordinarily rare still means eventually occurring. And if the universe lasts long enough in the dark era, with sufficient thermal fluctuations occurring, the statistical argument suggests that random configurations of matter that include conscious experiences would eventually appear. This is what Boltzmann and more recently cosmologists working on this question call the Boltzmann brain, and it raises a disturbing philosophical question that has become a genuine criterion for evaluating cosmological models. If your cosmological model predicts that Boltzmann brains will be statistically dominant observers in the universe over its entire history, more common than normally evolved observers like us, then it predicts that any given observer is more likely to be a randomly fluctuated Boltzmann brain than a product of normal biological evolution, which implies that all your memories are probably fake, which undermines the empirical basis of the theory itself. Most cosmologists treat the prediction of Boltzmann brain dominance as a sign that a cosmological model is wrong or incomplete, and use it as a negative criterion to rule out certain theoretical frameworks. Modern cosmological models that include dark energy and accelerating expansion may or may not avoid the Boltzmann brain problem depending on the exact nature of the dark energy and whether the universe eventually transitions into a different state or remains forever in a de Sitter-like accelerating expansion. There are recent and genuinely provocative results from the Dark Energy Spectroscopic Instrument, the DESI telescope, that are worth discussing here because they add a new layer of uncertainty to the long-term fate of the universe, and they are current enough to be relevant to the most up-to-date picture of what we know. DESI is a survey instrument mounted on the 4-meter Male telescope at Kitt Peak National Observatory in Arizona. It is designed to measure the three-dimensional distribution of galaxies across a huge volume of the universe by capturing the spectra of tens of millions of individual galaxies simultaneously and measuring their redshifts. The pattern of galaxy clustering on different scales, particularly a feature called baryon acoustic oscillations, which are frozen-in pressure waves from the early universe that serve as a standard ruler, can be used to measure how the universe has expanded over cosmic history. In its first data release in 2024, DESI found something genuinely unexpected. The data showed evidence at a level that statistical rigor requires to be taken seriously, though not yet considered definitive, that dark energy may not be a cosmological constant. It may not be a fixed energy density of empty space that remains constant over time. The DESI data hinted that dark energy's strength may have been different in the past than it is today. Specifically, it suggested that dark energy may have been somewhat stronger earlier in the universe's history and weaker today, or that its equation of state, the relationship between its energy density and pressure, has evolved over time. This is a potentially significant result. The cosmological constant model, also known as LCDM, has been the standard model of cosmology for about 25 years. It fits an extraordinary range of observations. But if dark energy is not a cosmological constant, if it is a dynamic field called quintessence that evolves over time, then the long-term fate of the universe changes. Some theoretical models involving evolving dark energy predict that dark energy will eventually reverse sign. Instead of driving the expansion of the universe, it will eventually become attractive. This would halt the cosmic expansion and reverse it, leading ultimately to a big crunch, a scenario in which the entire universe collapses back into a state of extreme density. In this scenario, the universe would not end in a cold, featureless heat death. It would end in a hot, violent collapse. The timescale for such a big crunch, if current data hints are correct, is deeply uncertain but could be measured in tens of trillions to hundreds of trillions of years rather than Google's. This would cut short many of the eras we have been describing. The degenerate era would be truncated, the black hole era might not arrive. The long, patient cooling of white dwarfs into black dwarfs, the slow evaporation of black holes through Hawking radiation over incomprehensible spans of time, All of it would be interrupted by a collapse long before those processes played out. It is important to be precise about the status of this result. The DESI data is intriguing and statistically significant enough to be published in major scientific journals and to attract serious attention from the cosmological community, but it is not confirmed. The systematic uncertainties in the analysis are real. Other measurements of cosmic expansion using different methods and different data sets are not yet fully consistent. The field is in active debate. The cosmological constant model has not been overthrown. It remains the standard model. The DESI results represent a hint, a crack in the consensus picture that warrants serious investigation and additional observational data. What the DESI results remind us of is something that the entire timeline we have been sketching depends on, and that we should hold clearly in mind. The long-term future of the universe is predicted by extrapolating physical laws that we have measured in the current universe across timescales of googles of years. If those physical laws change, if dark energy evolves, if new physics emerges at energy scales or timescales we have not yet probed, then the predicted future changes with them. This is not an excuse to dismiss the predictions. The predictions are the best available extrapolation of the best available physics, but it is a reason to hold them with appropriate scientific humility. The 100 trillion year boundary, the death of the last stars, that is among the most robust predictions of this framework. The exact nature of what happens in the black hole era and beyond is subject to greater uncertainty. Now let us step back from the physics for a moment and think about what all of this means from a different angle. Not the technical angle, but the existential one. You are right now at a particular position in the timeline of the universe. You are at 13.8 billion years after the Big Bang. You are in the middle of the stelliferous era. You are in approximately the middle of the era during which the universe is capable of producing and supporting stars. You are alive at a time when the universe is rich with free energy, when light pours from billions of galaxies, when the night sky is crowded with stars. Consider for a moment what that actually means. The physicist Avi Loeb and his colleagues at the Harvard-Smithsonian Center for Astrophysics have pointed out that from a pure probabilistic standpoint, a randomly chosen observer in the universe would be most likely to be found not now, but in the far future, close to the 10 trillion year mark, when the tiny, numerous, long-lived red dwarfs are at their peak, and the probability of life-bearing planets is statistically maximized by the enormous spans of time available for evolution and civilization building around each dim star. Life right now, in the early stelliferous era, with its massive stars and rapid stellar evolution, is almost premature by this statistical argument. Chances of life occurring at this stage of the universe's development are roughly 1,000 times lower than the probability of life occurring close to a red dwarf star deep in the stelliferous era. This is a strange thought to sit with. We exist in what might be called the early spring of the cosmos. The stars have not yet reached their long, slow summer. We are here first, so to speak, not because this is the most probable time or place for life, but because the early universe happened to produce the right conditions in a particular place in a particular galaxy, and because the physics of our particular planet and star was such that biological complexity arose on a schedule that landed us in the first few percent of the universe's star-forming history. The century we live in, the decade you happen to be reading this in, is an instant at the beginning of a story that has hundreds of trillions of years yet to unfold, and almost all of that story will unfold in darkness, in cold, in silence, with no new stars forming and most of the matter in the universe dispersed or locked in cooling remnants or consumed by black holes. We are not at the middle of cosmic history. We are not at the end. We are at the very beginning, in the period of greatest luminosity and complexity, before the long, slow, inevitable dimming. This should make the present moment feel different, not smaller, larger, because the alternative to appreciating it is to assume that the era of stars is permanent, that the universe will always look more or less as it does now, that the night sky you see on a clear dark night is the permanent background condition of the cosmos rather than an extraordinarily brief, extraordinarily specific, improbably structured window in an otherwise dark and cooling history. The stars are not the universe's normal state. They are its briefly flowering exception, and we are alive during the flowering. But let us go deeper into the mechanics of the dying, because understanding how the light actually goes out tells you something important about the nature of what remains. We said that red dwarf stars are the last to burn out. And that is true, but the process by which a red dwarf ends its life is worth describing in some detail, because it is so different from what most people imagine when they think about a star dying. A red dwarf does not explode. It does not expand into a red giant and engulf its planets. It does not produce a planetary nebula. It does not leave behind a neutron star. A red dwarf star, when it exhausts its hydrogen fuel, simply gets smaller and hotter. Here is why. Throughout a red dwarf's life, the core is being continuously resupplied with fresh hydrogen from the outer layers through convection. But this process cannot go on forever. As the hydrogen supply in the star dwindles, there comes a point at which the star's total mass is not sufficient to maintain the core temperature needed to sustain hydrogen fusion. But before that happens, as the hydrogen runs thin, the star passes through an interesting phase. The core contracts. The contraction releases gravitational potential energy which heats the star's interior. As the interior heats, the luminosity increases, the surface temperature rises. The star, counterintuitively, gets bluer and brighter as it approaches the end of its hydrogen-burning life. Astronomers have calculated that a dying red dwarf will spend hundreds of billions to trillions of years in this brightening phase before finally exhausting its hydrogen completely. Depending on the planet's orbit, this transition could actually move a planet from outside the habitable zone to inside it during the red dwarf's final billions of years of brightening. Eventually, the hydrogen runs out entirely. The star's core, no longer generating heat from fusion, begins to cool and contract. The star enters a white dwarf phase without any of the dramatic intermediate stages that sun-like stars go through. It simply shrinks. The outer layers do not expand away because there is no shell-burning phase to drive expansion. The star compresses into a helium-white dwarf, a dense, cooling remnant of mostly helium with a degenerate electron structure, and begins its long cooling into darkness. The very last stars to go through this process, the lowest mass red dwarfs with masses barely above the hydrogen-burning minimum of about 0.08 solar masses, will have lifetimes of up to 10 to 20 trillion years. At the 100 trillion year boundary, these stars are still burning. But by perhaps 50 trillion years, the star formation epoch has been over long enough and the gas supply has been depleted long enough that the very last red dwarfs have exhausted what little gas remained available to them when they formed and are winding down. There is also another route to the death of the last stars. Even without hydrogen exhaustion, there is a more mundane process at work. Gravitational interactions between stars in galaxies, those tiny perturbations we mentioned as drivers of galactic evaporation, can alter stellar orbits in ways that change stars' fates. Stars can be thrown into regions of high density where they interact with other stellar remnants. Two white dwarfs can collide, and if their combined mass exceeds the Chandrasekhar limit of about 1.4 solar masses, the merged object will detonate in a Type Ia supernova. Alternatively, a white dwarf in a binary system with a red dwarf can accrete hydrogen from its companion and detonate. These events are becoming rarer, but they still occur during the stelliferous era and produce the occasional brilliant flash of light in an otherwise dimming universe. There is something haunting about imagining those last Type Ia supernovae, explosions bright enough to outshine an entire galaxy for weeks, occurring in a universe where there are no astronomers to observe them, where the galaxies that once hosted them have dissolved through gravitational evaporation, where the nearest concentration of any kind of matter capable of receiving the information carried by those photons might be hundreds of millions of light years away. The light goes out in the darkness without witness. Before we proceed to the deepest future, let us spend some time thinking about what life and intelligence might look like in these remote epochs. Not because we know that life will exist in these eras, but because the question of whether it could, what it would require, and what it would experience illuminates something about the nature of the universe's future that purely physical description does not capture. The physicist Freeman Dyson, one of the 20th century's most visionary thinkers, wrote extensively about the long-term future and about the conditions required for life and intelligence to persist in a cooling universe. His 1979 paper, Time Without End, is one of the founding documents of what might be called physical eschatology, the scientific study of the universe's far future. Dyson's key insight was that life does not require a specific temperature or a specific substrate. Life requires the ability to process information and to use free energy to maintain organization against the tendency toward disorder. If those requirements can be met, life is in principle possible. And Dyson argued that in a universe with access to free energy gradients, even if those gradients are tiny and the temperatures involved are near absolute zero, some form of information processing organized structure could in principle persist. His argument for the stelliferous era and the degenerate era was that life should be possible throughout, as long as suitable environments exist. In the stelliferous era, life can exist around stars, obviously. In the degenerate era, life could, in principle, exist around slowly cooling white dwarfs, using the temperature difference between the white dwarf surface and the surrounding cold space as a free energy gradient to drive metabolism. The metabolism would be unimaginably slow by biological standards. The thought processes of any such civilization would occur on time scales of thousands or millions of years per subjective experience. But Dyson suggested, inspired by a scaling hypothesis, that the subjective experience of time might be no different from ours if the rate of consciousness scales with temperature. A cold-adapted civilization might subjectively experience its trillion-year existence as no longer than our own. This idea, the possibility of consciousness and civilization in eras completely unlike our own, persisting in forms completely unlike anything we know, is not scientific prediction. It is extrapolation of current knowledge into regimes far beyond anything we can test, but it is the kind of extrapolation that the best physical eschatology engages in honestly, because it forces the question of what exactly we mean by life and intelligence, and whether those concepts are more broadly applicable than our parochial biological definitions assume. Whether any form of life persists through the degenerate era depends on whether the gradients needed to drive information processing and maintain organization remain available. In the early degenerate era, cooling white dwarfs provide some free energy gradient. As they cool further and their surfaces approach the ambient temperature of the universe, that gradient diminishes. Eventually, if the ambient temperature of the expanding universe continues to decline, as it does with the continued expansion, the temperature differential between any source and the surrounding space becomes extremely small. The available free energy per unit time approaches zero. Whether life could adapt to operate on infinitesimally small free energy gradients is unknown. It involves questions about the minimum energy required for a bit of information to be processed and retained that we do not currently know how to answer. Rolf Landauer's principle establishes a minimum energy required to erase one bit of information related to temperature and Boltzmann's constant. At near absolute zero temperatures, this minimum is extremely small. It might be that some form of information processing could persist on incredibly slow timescales as long as the temperature is not absolutely zero, but the accelerating expansion of space creates a hard limit. In a universe expanding at an accelerating rate, as ours appears to be, the cosmological event horizon limits how much free energy any observer can ever access, even in principle, even with arbitrarily efficient technology. The total amount of information that can ever be processed by any civilization is finite, because the available free energy is finite, and because the minimum energy per computation, while small, is not zero. Freeman Dyson's original scenario of indefinite survival through infinitely slow computation may not be possible in a universe dominated by a positive cosmological constant, which is our universe. The accelerating expansion imposes a hard limit on the total amount of computation that any finite region of space can ever perform. This is a sobering conclusion. It means that if the current cosmological constant really is constant, then not only will all physical structures eventually decay, and all stars die and all black holes evaporate, but the total cognitive capacity of the universe, the total amount of thinking that any intelligence or intelligences could ever do across all of cosmic history, is finite. There is a maximum amount of computation that can ever be performed, a maximum number of thoughts, a maximum complexity. Whether this is a tragedy or simply a fact about the universe's structure depends on your perspective. It is certainly not a practical concern for any civilization operating on geological or even astronomical timescales. But as a statement about the ultimate nature of reality, about whether the universe's story has a final page, it carries weight. Let us return now to the most uncertain and fascinating piece of this entire picture: dark matter. We have not said nearly enough about dark matter, and that is partly because what can be said about it with confidence is limited. Dark matter constitutes about 27% of the energy content of the observable universe. It does not emit light, does not absorb light, does not interact electromagnetically with anything we can directly detect. We know it exists because its gravitational effects are observable in the rotation of galaxies, the gravitational lensing of light by galaxy clusters, the large-scale structure of the cosmic web, and the acoustic oscillations in the cosmic microwave background. What dark matter is made of is one of the central unsolved problems in physics. The leading candidates over the decades have included weakly interacting massive particles, also called WIMPs, which would interact through the weak nuclear force and gravity. Axions, very light particles predicted by some extensions of the Standard Model. Sterile neutrinos, hypothetical particles that interact only gravitationally. Primordial black holes that formed in the very early universe. Other possibilities include more exotic theoretical entities. Despite decades of searching in underground direct detection experiments, at particle accelerators, and in astrophysical observations, dark matter particles have not been directly detected. The WIMP miracle, the coincidence that suggested WIMPs with properties similar to supersymmetric particles would naturally give the right relic abundance to account for dark matter, has been significantly constrained by null results in detection experiments. The most sensitive direct detection experiments have excluded large regions of parameter space without seeing a signal. This means the nature of dark matter is genuinely unknown, and the uncertainty about its nature introduces uncertainty about its fate in the far future. If dark matter consists of particles that are stable indefinitely, they will persist through the dark era as individual particles drifting through the expanding darkness. They interact only gravitationally and possibly through the weak force. In the dark era, with essentially no matter density and vast separations between particles, Even gravitational interactions would be extraordinarily rare. Dark matter particles would essentially never encounter each other. They would persist individually, each on its own, nearly straight path through an expanding void. If dark matter particles have some finite lifetime, they will decay. The products of their decay would contribute to the radiation bath of the dark era. If dark matter consists of primordial black holes, they will evaporate through Hawking radiation on timescales determined by their mass, contributing to the Hawking radiation that slowly fills the dark era universe before dissipating. In any case, dark matter participates in the long-term evolution of the universe primarily as a gravitational actor during the stelliferous and degenerate eras, shaping the structure of galaxies and galaxy clusters, and then fading in importance as matter disperses and black holes consume the available mass. There is a process we should address that sits at the edge of theoretical uncertainty, but is important enough in the cosmological future that it cannot be omitted. The ultimate fate of black dwarfs if protons are stable. We said earlier that if proton decay does not occur, black dwarfs persist through the degenerate era. But there is another process that will eventually act on them, one that is even slower than proton decay, but that is guaranteed by quantum mechanics to occur given sufficient time. It is called quantum tunneling to iron. Iron 56 is the most stable atomic nucleus. It has the lowest binding energy per nucleon of all the elements, meaning it takes more energy to split iron into lighter components than it releases, and it releases energy when heavier elements fuse down to iron or lighter elements fuse up to iron. Iron 56 is the thermodynamic ground state of nuclear matter. Given infinite time, all nuclei should want to convert to iron 56. White dwarfs are made primarily of carbon-12 and oxygen-16. These nuclei have higher energies per nucleon than iron 56. In principle, they should fuse to iron, but at the temperatures and pressures inside a white dwarf, classical nuclear fusion does not occur because the temperature is far below what is needed for thermonuclear reactions. The nuclei stay as carbon and oxygen because the energy barrier to fusion is too high for them to cross classically, but quantum mechanics allows particles to tunnel through energy barriers without having enough classical energy to surmount them. Given enough time, even a carbon nucleus has some non-zero quantum mechanical probability of tunneling through the barrier and participating in a fusion or decay process that moves it toward iron 56. The timescale for this process is staggering. Various estimates put the tunneling timescale for carbon to iron conversion at something like 10 to the power of 10 to the 26 years. Written in the only way that conveys the absurdity, this is a 1 followed by 10 to the 26 zeros. This makes proton decay look immediate by comparison. Proton decay, which we described as potentially occurring over 10 to the 37 years, would have finished billions upon trillions of times before quantum tunneling had even begun to have a statistically significant effect on a typical black dwarf carbon nucleus. If protons are stable, black dwarfs will eventually, over time, scales that reduce the cosmological century of a googol of years to a complete irrelevancy, convert their carbon and oxygen to iron through quantum tunneling. A black dwarf made of iron 56 in a degenerate electron gas is at a lower energy than one made of carbon and oxygen, so the process is thermodynamically favored. It is just quantum mechanically slow. After the nuclear conversion is complete, however, the iron 56 black dwarf faces another quantum mechanical process. An iron 56 nucleus in a dense electron gas can capture electrons in a process called inverse beta decay, converting protons to neutrons. As the iron absorbs electrons and its nucleus becomes increasingly neutron-rich, the black dwarf collapses. Without the electrons in the Fermi sea to provide degeneracy pressure, the support against gravity fails. The black dwarf collapses inward until it becomes a neutron star. But the neutron star, too, is not stable over infinite time. If protons are stable, neutrons can still decay through quantum tunneling via a process that converts the neutron star to a smaller, denser state. Eventually, through a series of tunneling processes at timescales even more astronomically remote than the carbon-to-iron conversion, black dwarfs that avoided dissolution through proton decay will ultimately collapse into black holes, which will then evaporate through Hawking radiation. Every path leads to the same destination. The matter either decays through proton decay or converts through quantum tunneling to iron and then collapses. Either way, eventually nothing remains except the radiation products of all these processes spread across an unimaginably vast and cold universe. It is worth pausing at this point to consider the role of gravity in all of this, because gravity is in some ways the engine that drives the entire narrative we have described. Gravity formed the stars from primordial gas clouds. Gravity maintains the stars against the outward pressure of fusion for their main sequence lifetimes. Gravity causes the stars to collapse into white dwarfs, neutron stars, and black holes at the end of their lives. Gravity organizes stars into galaxies. Gravity causes galaxies to merge and evolve. Gravity governs the dynamics of galactic evaporation. Gravity feeds the supermassive black holes. Gravity, through general relativity, determines the curvature of space-time that allows black holes to exist, and that governs the Hawking radiation through which they eventually evaporate. Gravity, through its interaction with quantum fields, produces the Hawking effect that ends the black hole era. And in the far future, gravity is absent, not because it ceases to exist, but because the objects it acts on have become so sparse and so distant from each other that gravitational interactions between them are effectively nil. In a universe of extreme density, gravity is dominant. In a universe of extreme dilution, gravity is a whisper so faint it registers on nothing. The Dark Era universe is one in which gravity has essentially retired. It has done its work across googles of years. It has shaped and rearranged and ultimately dispersed everything. And now the universe exists in the state that gravity's work has produced, a state so uniform and so cold and so empty that gravity has nothing left to do. This is the gravitational arc of cosmic history. From the dense, hot, structured early universe through the complex middle era of stars and galaxies and black holes, and the long, slow cooling of the degenerate era, and the evaporation of the black hole era, gravity has been the organizing and then the dispersing force, and it ends having organized the universe out of complexity and into emptiness. Alternative endings deserve attention here, because the heat death scenario, while the most widely accepted, is not the only possibility that physics presents. We have mentioned the Big Crunch, the possibility that dark energy evolves or reverses, causing the expansion to halt and reverse into collapse. If this happens, the universe ends not in cold emptiness but in hot density. The Big Crunch scenario runs the cosmic expansion backward. Galaxies approach each other. Stars are heated by the radiation of neighboring stars as they crowd closer and closer. Eventually, the average background temperature of the universe exceeds the temperature of stellar surfaces, at which point stars cease to radiate effectively and are instead in thermal equilibrium with their surroundings. The cooling and compressing continues. Nuclear physics changes as temperatures rise to conditions similar to those in stellar interiors, then similar to those in the Big Bang itself. Everything dissolves into a plasma of quarks and gluons, and then, in the models, reaches a singularity. Whether the Big Crunch singularity is truly a singularity, or whether quantum gravity effects smooth it out into a bounce that produces a new cycle of expansion, is one of the deep speculative questions of physical eschatology. Roger Penrose's conformal cyclic cosmology suggests one mechanism by which the end of one cosmic era could serve as the beginning of another. Loop quantum cosmology offers another framework in which the Big Bang itself may be a bounce from a prior contracting phase. These ideas are theoretically motivated but not observationally confirmed. There is also the possibility of a big rip. If dark energy is not a cosmological constant but a dynamic field called phantom dark energy, with an equation of state parameter less than -1, then the energy density of dark energy increases as the universe expands. This means the force driving the expansion gets stronger over time, not just because the volume is larger, but because the dark energy density is actually increasing. This leads to a scenario in which the expansion accelerates without limit, eventually causing the separation of all structures regardless of how strongly they are gravitationally bound, not in hundreds of trillions of years, but on a finite time scale that some models put at somewhere between 10 billion and 20 billion years from now. In the Big Rip scenario, the expansion tears apart galaxy clusters, then galaxies, then star systems, then individual planets, then atoms, in a sequence of increasingly small structures being ripped apart by the expansion as its rate grows without bound. The universe ends not in cold emptiness, but in an expansion so violent that it destroys all structure down to the subatomic level at a finite time in the future. Current data does not favor the Big Rip. The best current measurements of dark energy's equation of state parameter suggest it is consistent with -1, the cosmological constant value, possibly with slight deviations in the direction the DESI results hint at. Phantom dark energy with an equation of state below -1 is not ruled out but is not preferred by the data. The Big Rip remains a theoretical possibility, not a leading prediction, and there is another possibility entirely, the Higgs vacuum. The universe we inhabit has a Higgs field that permeates all of space. The Higgs field is what gives elementary particles their masses through the Brout-Englert Higgs mechanism. The Higgs field has a specific value throughout the universe, what physicists call its vacuum expectation value. But this value may not be the true minimum energy state of the field. It may be a metastable false vacuum, a local minimum in the energy landscape of the Higgs field that is not the global minimum. If this is the case, then the Higgs vacuum could quantum tunnel to its true ground state at any point in the universe's future. The tunnel would produce a bubble of true vacuum that expands outward at the speed of light. Inside the bubble, the laws of physics would be different, because the Higgs field having a different value means elementary particle masses would be different. The bubble would be invisible from outside, arriving at any location at the speed of light, and therefore giving no warning. Everything inside the bubble would be instantly and completely restructured at the fundamental physical level. The status of this vacuum instability is genuinely uncertain. Calculations based on the measured mass of the Higgs boson, which was discovered at the Large Hadron Collider in 2012, suggest that the Higgs vacuum may be metastable rather than fully stable. The lifetime of the metastable vacuum, if this interpretation is correct, has been estimated at somewhere around 10 to the 100 years, similar to the timescale of black hole evaporation, though with enormous uncertainties. Some analyses suggest the vacuum may be fully stable given other inputs to the calculation. The question remains open. If the Higgs vacuum is metastable, and if the universe eventually tunnels to the true vacuum, the transition would end the history of the current physical universe in a way completely different from any of the scenarios we have discussed. Not a heat death, not a big crunch, not a big rip, but a restructuring of the laws of physics themselves across the entire universe as the true vacuum bubble expands. We are now in a position to try to draw together the threads of this exploration and say something about what it all means, not just physically, but in terms of what it tells us about our existence right now. The universe is approximately 13.8 billion years old. The last stars will die approximately 100 trillion years from now. That is a factor of roughly 7,250 in the remaining star-forming lifetime of the universe, compared to the age we currently live at. We are less than 0.014% of the way through the era of stars. That figure, less than 1% of 1%, deserves to sit with you for a moment, not because it should produce despair. Despair is a response to personal loss, to the termination of things you care about in timescales relevant to your life. The death of the last star in 100 trillion years is not a loss in any human sense. No one will experience it as a loss because no one whose consciousness is continuous with our own will be alive to experience it. The scales are simply too different. But the figure should produce wonder, and a specific kind of wonder that is different from the usual cosmic wonder that comes from contemplating how large the universe is in space. The wonder that comes from contemplating how large it is in time. Space already does this to us. We look at the night sky and feel something shift in our sense of scale when we realize that the light from the stars we see has been traveling toward us for years or decades or centuries or millennia. We feel the vertigo of distance. We feel the strangeness of looking across intervals that dwarf everything familiar. Time should do the same thing. The 100 trillion year horizon should produce the same vertigo, the same strangeness, the same shift in how we hold our own existence. Because we are not at the end of cosmic history, we are impossibly early in it. The universe, if it lasts to the heat death, will be a heat death universe for durations that make the entire era of stars look like the first second of a human life. And within all that time, in all those eons and epochs and cosmological decades that stretch from the death of the last star to the evaporation of the last black hole to the cooling of the dark era into its final featureless equilibrium, the universe will be empty and dark and cold and silent. There will be no light falling on any surface. There will be no surfaces in any meaningful sense. There will be no complex structures generating free energy and doing work and maintaining organization. There will just be the dispersed radiation and the drifting particles and the expanding void and the slow approach to maximum entropy that the second law of thermodynamics has been working toward since the beginning. We are at the only moment when the universe is interesting. Not interesting in the sense of being pleasant for us personally, though it is that too, but interesting in the objective, physical sense of having concentrations of free energy and structural complexity and steep thermodynamic gradients that allow interesting things to happen. We are at the flowering, the very brief, improbably intense, improbably complex era of stars and planets and chemistry and life and civilization and consciousness that sits at the beginning of a cosmic history that stretches to timescales that make a Google look small. This is a strange thought, but I think it is an honest one. Let us now spend some time on the specific milestones in this timeline, laid out with as much precision as current science allows. At 5 billion years from now, the Sun leaves the main sequence and begins its red giant phase. Earth's surface conditions become uninhabitable for complex life well before this, around 1 billion years from now, as the Sun brightens and Earth's oceans begin to evaporate. This is not a sudden catastrophe. It is a gradual planetary change driven by stellar evolution. At approximately 5 billion years, the Sun has reached its maximum red giant size and is beginning to expel its outer layers, which will form a planetary nebula. Whatever remains of the solar system will cool under the light of the Sun's white dwarf remnant, a dense sphere about the size of Earth with a surface temperature initially of perhaps 100,000 Kelvin, slowly cooling over the following billions of years. At approximately 4.5 billion years, roughly simultaneous with the Sun's red giant phase, the Milky Way and Andromeda begin their merger. The merger takes several billion years to complete, resulting in the elliptical galaxy Milkomeda. At 10 billion years, the Sun's white dwarf remnant has cooled to tens of thousands of Kelvin, still hot by human standards, but no longer a significant source of radiation for any remaining objects in its vicinity. The Milky-Meter merger is complete, and the merged galaxy has settled into a large elliptical structure. At 100 billion years, nearly all galaxies outside the local group have been carried beyond the cosmological event horizon by the accelerating expansion. The sky, as seen from Milky-Meter, contains primarily the merged remnants of local group galaxies. Star formation has declined dramatically but has not ended. The brightest stars remaining are mainly red dwarfs. At 1 trillion years, star formation has slowed to a fraction of its current rate. The population of white dwarfs is enormous. The universe is dominated by the combined faint red glow of billions of red dwarfs and the slowly cooling white dwarfs from stars that died long ago. At 10 trillion years, the most massive red dwarfs, those with masses around 0.5 solar masses that have lifetimes of tens of trillions of years, are beginning to exhaust their hydrogen. They cycle through their end state and become helium-white dwarfs. The universe's stellar population is thinning. Still, billions of red dwarfs burn, but the decline is visible in the numbers. At 100 trillion years, the last star formation has ended. The free gas supply is exhausted. The remaining stars are the lowest mass red dwarfs, those with the longest lifetimes. These are burning very faintly in the deep infrared. The degenerate era is beginning to arrive. At approximately 1 quadrillion years, the last of the low-mass red dwarfs have exhausted their hydrogen. They have passed through their blue dwarf phase and settled as cooling white dwarfs. The stelliferous era is over. The universe is dark except for the faint glow of white dwarfs at various stages of cooling and the even fainter Hawking radiation of black holes. At roughly 10 to the 23rd years, galactic evaporation has essentially completed. The organized structures we call galaxies have dissolved. Stars and stellar remnants have either been ejected into intergalactic space or consumed by supermassive black holes. The supermassive black holes of former galactic centers are the dominant mass concentrations. If proton decay occurs at around 10 to the 34th to 10 to the 37th years, all black dwarfs and neutron stars have dissolved. Normal matter in any form no longer exists. The universe consists of the dispersed products of proton decay, low-energy photons and leptons along with black holes. If proton decay does not occur, normal matter persists in the form of cold black dwarfs drifting in intergalactic space, subject eventually to quantum tunneling processes on timescales far longer than the proton decay timescale. At approximately 10 to the 40th years, the beginning of the black hole era, stellar mass black holes have either consumed available material or formed from the collapse of normal matter that underwent proton decay or quantum tunneling collapse. The universe is entirely black holes, radiation, and dispersed particles. The black hole era spans an enormous range of time. Stellar mass black holes evaporate on timescales of around 10 to the 74th years. Supermassive black holes of billions of solar masses take until around 10 to the 97th years. The most massive black holes take until around 10 to the 100th years, a googol of years. Each evaporating black hole emits its Hawking radiation into the surrounding cold universe, contributing a brief burst of energy to the darkness. In the final moments of a black hole's life, the Hawking temperature rises to enormous levels as the mass decreases, producing a bright, brief flare of high-energy particles. These final evaporation events are the last bright phenomena in the universe, isolated events separated by enormous intervals of darkness. By the end of the black hole era, roughly at 10 to the 100th years, all black holes have evaporated. The universe contains only the diffuse products of all those evaporations, an extremely cold, extremely low-density thermal bath of photons, neutrinos, and possibly other particles. The dark era has begun. In the dark era, the universe approaches maximum entropy. There are no structures, no concentrations of matter, no temperature gradients, nothing to see, nothing to measure time by in any conventional sense. The universe exists in something approaching thermodynamic equilibrium, at a temperature extraordinarily close to but not quite zero, expanding without limit, becoming ever more dilute. This is where the standard cosmological future ends. What about time itself? Does the dark era change what time means? This is a question that physics can partially address. We said earlier that the flow of time, the felt experience of one moment following another, is connected to thermodynamics. The arrow of time, the sense in which the future is different from the past, is rooted in the second law of thermodynamics. The past has lower entropy than the future. Things tend to become more disordered over time. We remember the past and not the future because the past was lower entropy, and lower entropy states tend to leave records and traces in higher entropy, later states more readily than the reverse. In a universe at maximum entropy, this arrow of time disappears, not because physics becomes time-symmetric in any new sense, but because the distinction between past and future loses practical content. There are no records to refer to, there is no memory, there is no organization that was previously created. In a universe of maximum entropy, every moment is the same as every other. Nothing marks time's passage. The universe is, in this sense, timeless, not because time stops, but because there is nothing to measure it by. The Wheeler-DeWitt equation, the equation that in the framework of quantum cosmology describes the quantum state of the universe as a whole, famously contains no time variable. We discussed this in the context of the problem of time in quantum gravity. In the dark era, the universe approaches a state where the classical arrow of time has dissolved, and the deeper timelessness of the underlying quantum description emerges from the fog of ordinary physics. Whether this means anything philosophically or practically is a question that physics alone cannot answer, but it is a question worth sitting with. The universe began in a state of extraordinarily low entropy, the precise and specific nature of the initial conditions that set the arrow of time running. That arrow has been pointing in the same direction for 13.8 billion years, and will continue to do so through the entire stelliferous era and the degenerate era and the black hole era. But in the dark era, as entropy approaches its maximum and the gradient that drives the arrow flattens to nothing, something fundamental about the structure of time itself dissolves. Let us close by thinking about the deepest question this entire story raises. We have followed the universe from now to the death of the last star and beyond. We have traced the cooling of white dwarfs, the evaporation of black holes, the dissolution of matter. We have described the dark era, the heat death, the approach to maximum entropy. And throughout all of it, we have been assuming that the physics we know today, the laws of general relativity, quantum mechanics, thermodynamics, the standard model, remains valid on the timescales involved. That assumption may not hold. We already know that our current physics is incomplete in ways we can identify. General relativity breaks down at singularities. Quantum mechanics and general relativity are incompatible at Planck energies. The nature of dark matter is unknown. The origin and ultimate fate of dark energy is unknown. What happened before the Big Bang, if before, is even a meaningful concept in that context, is unknown. Whether protons decay or are stable is unknown. Whether the Higgs vacuum is stable or metastable is unknown. On timescales of googles of years, the probability that our current physical theories remain exactly accurate without modification is essentially zero. New physics will emerge or has already emerged at energy scales we have not yet probed that modifies the picture. The question is whether those modifications change the broad outline significantly or only the details. The broad outline that the universe has a finite reservoir of free energy that is being irreversibly consumed, that entropy increases, that the stars are burning fuel they cannot recover, that the expansion continues and accelerates, that these trends lead eventually to a cold, dark, empty, maximum entropy universe is extremely robust. It follows from the second law of thermodynamics, which is one of the most firmly established principles in all of science. The specific timescales and mechanisms can change. The general direction is, as far as we currently know, fixed, unless the big crunch occurs, unless the big rip occurs, unless the Higgs vacuum tunnels, unless new physics entirely beyond what we can currently conceptualize changes the picture. These are real possibilities. The future is genuinely uncertain, but the direction, absent these dramatic alternatives, is clear. The universe trends toward equilibrium, always has, always will. And against that background, the present moment glows with a particular intensity. Right now, hydrogen is fusing to helium in the core of the Sun. Right now, 100 billion other stars in the Milky Way are doing the same thing. Right now, across the 2 trillion or so galaxies of the observable universe, an uncountable number of stellar fusion reactors are burning. Right now, the free energy released by all that burning is cascading through complex systems, maintaining temperature gradients, driving chemistry, powering biology, enabling thought. Right now is when it is happening. This slice of cosmic time, thin as it is in the full timeline, is the moment when the universe is most complexly organized, most structurally rich, most capable of hosting interesting processes. The photons leaving the Sun right now and falling on this planet right now and driving the photosynthesis that ultimately powers every living thing on this planet right now are the latest in an unbroken chain of free energy usage that stretches back billions of years and will stretch forward in diminishing form for trillions more. In 100 trillion years, the last of that chain will end. The last red dwarf will exhaust its last hydrogen atom. The last nuclear fire in the universe will go out, and the long, dark, cold future will begin. It is worth asking yourself how you feel about that. Not whether you are afraid of it. You will not be there. Not whether it makes the present seem meaningless. It does not, for reasons we have explored, but whether it changes how you hold the present moment. Whether knowing that the stars are mortal and that their mortality operates on a time scale so vast, it defeats human intuition, while also being finite and bounded, changes anything about how you experience this particular fire in the sky. I think it should. Not in a way that produces existential crisis, but in a way that produces gratitude for the specificity of now. You exist in the era of stars. You are alive during the flourishing. You can look up on a clear night and see not just light but time, the specific moment in cosmic history when matter has organized itself into burning spheres that pour free energy into space, when that free energy has cascaded into chemistry and biology and culture and curiosity, when a piece of the universe has become conscious enough to ask what the rest of the universe is doing. That window is not permanent, it is finite, it is measured in trillions of years from here, which is an enormous amount of time by any human measure, but it is bounded. The era of stars will end. The era of complexity built on stars will end with it or shortly thereafter. And what follows is longer and darker and colder and quieter than the mind easily holds. This is the universe, not as a setting for human stories, though it is that, not as a backdrop for civilization, though it is that too, but as a physical system with a history and a future and a trajectory written in its laws, tending always toward the equilibrium it has been approaching since the moment it began. The stars are not the default, they are the exception. The brief, brilliant, improbable exception, burning against the cold and the dark that is the universe's ground state, its beginning and its end. In 100 trillion years, the exception ends, and everything after that is the ground state, extending without limit, cold and dark and featureless, for longer than any star ever shone, for longer than there are words to express. That is what is waiting. That is where we are going. And understanding that, really holding it even approximately, even for a moment, changes something about how you see the light falling through the window right now. It comes from a burning sphere of hydrogen that has been shining for 4.6 billion years and has 5 billion more to go. It is not permanent. It will not always be here. Nothing in the universe burns forever. But right now, it is burning. And that is not nothing. That is, in the deepest physical sense available to us, the whole improbable point.